Hello everyone, welcome back to the latest lecture session. Let's look at what we were discussing in the previous session. We were discussing about the quality of wastewater and the relevant parameters that we are typically concerned with, right? Let's have a quick recap. We were primarily concerned with four major parameters. In the context of organics, we say or we try to understand them or measure them in terms of oxygen demanding materials. So, biochemical oxygen demand typically over a 5-day period, and the chemical test COD, chemical oxygen demand, typically takes 2 hours to 3 hours, right, including setup time it takes 3 hours. So, nutrients, we were concerned with nitrogen and phosphorus, right. Why is this? Why were we concerned with nitrogen and phosphorus? I guess we were talking about issues with respect to algal bloom, and I believe we looked at that in relatively greater detail, right. And as I mentioned, or as we discussed, in inland surface waters, phosphorus is typically the limiting nutrient. In oceans and such, it is typically nitrogen. And in that context, we saw how nitrogen can be bound to organic compounds, right. Amines and such, proteins and so on and so forth are the sources. So, we also have the forms in terms of ammonia, let us say, right, that is something that we have. So, obviously, after oxidation or oxidation, pardon me, what can they be transformed into? NO2 minus or nitrite or nitrates, let us say, right. So, one aspect to note is that nitrates are regulated compounds in drinking water. As in, if I take in nitrates at a concentration greater than the threshold that is mentioned in the relevant standard for a given period of time, I will observe adverse effects in my body or in my health. Typically methemoglobinemia, where you have the blue baby syndrome, that is an issue with respect to nitrates. So, you obviously do not want to have a lot of nitrates in your particular solution, and thus we are going to look at removal of nitrogen, let us say, right. And suspended solids and pathogens, we will discuss that in detail or relative detail today. Before we go further, what were we talking about in the context of nitrogen? We talk about ammonia or total ammonical nitrogen, let us say, typically expressed as N, units are typically as N in milligrams per liter typically, and then the oxidized forms nitrite and nitrate, depending on the source and more importantly depending upon the time available, you might have a combination or typically will have a combination of both this reduced forms and oxidized forms of nitrogen. Obviously, if oxidized forms of nitrogen are predominating, that can mean that the waste has been around for quite some time, and the degradation or oxidation has been taken place or has been occurring, right. And then obviously, we have the total inorganic nitrogen, as the name indicates it is inorganic, that is why you do not have any organic content, as in no C, let us say, no carbon. So, we have the relevant inorganic nitrogen, and then total Kaldal nitrogen, which is going to measure the organic N, right, organic N, and then the reduced forms of nitrogen, and then organic nitrogen too. But how do you differentiate between total Kaldal nitrogen and organic nitrogen? Both depend on the Kaldal method, but in the measurement of organic nitrogen, we try to remove the ammonia from the relevant solution, typically by boiling, let us say, and allowing for change in phase. Obviously, you need to look at the pH too, right. And another aspect to note is that to convert or not note, to look at is that when we are trying to look at organic nitrogen, we then digest this particular organic N, right. It is bound to the organic compounds. You want to break these particular bonds, and you typically look at digestion by applying acids and maybe some heat, let us say, right. So, that is something to keep in mind. Typically, we are concerned with TKN, let us say, right, TKN. And then I believe we were looking at phosphorus. In the context of phosphorus, we looked at the 3 aspects, right, but typically we looked at orthophosphates as being of primary interest to us, right, as in H2PO4 minus, HPO42 minus, PO43 minus and such, right. Why is that? Because they are easily soluble or very soluble and easily relatively more reactive, as in the relevant bacteria can make use of these relatively soluble compounds relatively easily. And what are the other forms? I guess we have polyphosphates, where we have what do we say, more than one phosphorus and such, and then the organically bound phosphates, but these are relatively less soluble and also relatively slow to hydrolyze and thus be degraded or be used, I guess, by the microorganisms. That is something to keep in mind, right. Nitrogen and phosphorus. And then we are going to look at suspended solids now, right. But why do I care about suspended solids? Well, if I am having bigger particles, let us say, which are suspended and such, that by itself can create issues in my system or even aquatic system. They can aquatic ecosystem, they can interfere in the, or be deposited on the gills of the fish and such. You will have such issues and obviously digestive tract issues. Another aspect is that these suspended matter, these matter or particles suspended in the water, right, they are going to act as possible carriers or sites for microbial growth or even virus, let us say, right. So, you do not want to have what we say surfaces where the microbes can grow on, but if you have a lot of suspended solids, that is one particular aspect to be concerned about, right, growth of microbes, let us say. And let us look at how it is that we are going to what do we say, measure this suspended solids or different solids, let us say. Why just talk about suspended solids? Though I am talking about suspended solids here, we are going to look at solids and then suspended solids. Let us move on. So, here we have the sample, right. One aspect is the settlable solids. We have an Imhoff cone, right, something like this, and after a particular time you will see up to a particular depth how much has settled. So, settleable solids, as in within a reasonable period of time, how many solids can be, or how much of the solids can be removed from your water by gravity itself, right, that is settleable solids. And if I am not just concerned about settleable solids and I want to look at the total solids, obviously, right, what do? I am going to evaporate it, put it in an incubator or oven at around 100 or 105 degrees centigrade, right, and then I am going to evaporate it, right, and I will get the total solids in that particular beaker, right. I will weigh the beaker before and after and I will get the relevant concentration, not concentration, pardon me, mass, and then you know the volume of water you used. So, you will get mass per volume, right, mass per volume, and you will be able to get your relevant total solids, right. TS is for total solids. And then if I want to dig deeper, which is what we are always concerned about, at least in this course or in wastewater treatment, I want to look at suspended solids and dissolved solids. Why is that? Well, I guess it is because different unit process tackle different kinds of solids. Total suspended solids, let us say, are typically going to be removed during primary treatment. Dissolved solids typically during your biological process, where the bacteria are going to try to degrade your dissolved solids, right. So, we need to be able to understand the relevant variables to be able to design for our wastewater treatment plant. So, suspended solids, let us see how you will get it. So, obviously, we are talking about suspended, right. So, you need to filter it through a particular glass fiber filter. And in this context, whenever you are reporting the suspended solids or the dissolved solids, let us say, you are typically going to have to mention the size of your filtrate or filter size, let us say, right. Is it 0.45 microns, 0.2 microns or such? Because if the size is smaller, right, most of it we will say is what do we say, most of it might not pass through, right, or lesser fraction will pass through. But if the size of my filter is larger, more of it will pass through and I will classify that as suspended, right. So, that is one thing to keep in mind. So, total dissolved solids in that context, let us say, right. Again, if I did not spell it out wrong, let us say if this is my filter, again this is not how the filter is going to look like. We are talking about remarkably low sized what do we say, filters, glass fiber filters. So, if I take a smaller one, so as we just discussed, the size of the relevant glass fiber filter has to be mentioned when we are mentioning the total dissolved solids or such, let us say, right. That is something to keep in mind, right. So, let us move on and understand this in somewhat greater detail. So, I have a known volume of sample, let us say I am calling that V, and then I am going to pass that through this particular filter 0.45, 0.2 or different particular filter, right, and so, it is going to pass through that particular filter, right, as in particles of size less than the filter size, let us say, or the pore size will pass through that particular filter, and I am going to collect that in a particular beaker. I am going to collect the water in a particular beaker, right. So, this I will put in an oven and let us say at a temperature of around 105 degrees centigrade or 100 degrees centigrade, and I will let the water evaporate out. So, at the end of, let us say, day or so or the relevant period, I will just be left with the total dissolved solids, let us say, right. Obviously, if I did not filter it, I would have just gotten total solids, right. This way I will get the total dissolved solids, right. And typically sometimes people take the difference to measure the total suspended solids, or you can look at what was collected on your filter. Let us say you can look at what is collected on your filter and measure the difference, let us say, before and after filtration. When I say difference, the difference in weight of your filter, let us say, right, and then you will get your total suspended solids. Yes, so that is one way, but if you want to rule out the error, I guess this is a better way, but in general you always need to take a greater volume. If not, you will run into issues with respect to accuracy, let us say, because we are talking about, let us say, 200 milligram per liter, or in the case of groundwater, the TDS or TSS, pardon me, will be much lower. So, you need to be really careful when you are trying to measure it based on the kind of water or sample you are measuring. Let us move on now. So, I am done with dissolved solids and suspended solids. Now, we are going to look at the organic content in my particular sample, which I am going to say is going to be measured by putting the sample in a muffle furnace at around 550 degrees centigrade for a given period of time. So, that is what I have, muffle furnace or muffle oven, let us say. So, whatever is left in here, right, this is the total dissolved solids, but I want to look at it further. I want to classify it further as volatile dissolved solids and fixed dissolved solids. Where do I have that? Volatile dissolved solids, fixed dissolved solids. So, volatile dissolved solids, they more or less mean the organic content. That is what it is, that is what we are trying to measure when we say it is volatile dissolved solids. So, when I increase the temperature and maintain it at 550 degrees centigrade, so most of it is going to, what we say, I should not use the term burn, but you understand what I am trying to say out here, right. So, the organic content is not going to be out there, and that difference will be the volatile dissolved solids. But what is left inside your particular beaker or petri dish after you maintain the temperature at 550 degrees centigrade will be the fixed dissolved solids, typically relatively inert or inorganics and such, let us say, right. That is one particular aspect. Similarly, for the suspended solids also, you can measure the volatile and the fixed suspended solids, right. Again, we are trying to get an idea about organic content that is suspended, organic content that is dissolved, let us say, right. So, that is one aspect to look at, and obviously total volatile solids we have that, and total fixed solids again, right, again just general summation out here with respect to both the suspended and dissolved, let us say, right, or you can even probably look at it directly from this sample. And obviously, this total should be equal to the total solid which we would have or we get from out here, let us say, right. So, again, why are we looking at suspended solids, dissolved solids, and again volatile solids and fixed solids and such, because each unit process is going to look at removal of certain kind of what do we say, material or such, let us say. For example, primary treatment, we are looking at removal of suspended solids, right, or settlable solids. If not, we will add a coagulant and then let them flocculate and then settle down by gravity, right. So, we are going to look at suspended solids in that context. And again, in the context of biological treatment, my major focus is going to be on the dissolved organics, let us say, right. I am going to try to remove the dissolved organic content. So, thus I need to be able to measure the different what do we say variables that we just listed out here. And I believe then we are going to look at pathogens, right. I believe we discussed this at the start of the course, but let us just try to refresh our memory. Again, pathogens, right, microorganisms capable of causing disease, that is what we have. General aspect, pathogenic, I should not have used the term pathogenic microorganisms. So, microorganisms, right, we see the evolution and such, yes, 3 billion years ago. So, bacteria and archaea, right. Please do not what do me say, or how do I say this, use me as a reference for pronunciation, and we call the bacteria and archaea together as prokaryotes, and the bigger and more complex forms as eukaryotes, let us say, right. And what is the difference between bacteria archaea on one hand and this eukarya on the other hand? Well, in this particular prokaryotes, which encompass bacteria and archaea, right, we have, or they are relatively simpler life forms, unlike the eukarya, let us see, right. I believe I have a picture out here, but we will go through that, or we will look at that. Here the chromosome, let us say, in bacteria and archaea is not within a nucleus, and in eukarya it is going to be within a nucleus. That is one particular difference, pardon me. And here what are the typical pathogens? Protozoa, yes, and gram positive bacteria, protobacteria, or these bacteria that we already mentioned out here. And typically in archaea there are no known pathogens, right, but compounds, not compounds, pardon me, archaea or microorganisms of interest include methanogens. As the name indicates, it is what do we say, the final product is going to be methane, and that is typically used in anaerobic treatment, let us say. Anaerobic as in process occurring in the absence of oxygen, anaerobic, right. And in that process, let us say, it is the methanogens that play a considerable role or the major role, right. So, that is why I guess we highlighted that. Again, no known pathogens among archaea, right, and yes, we do have a lot of known pathogens within bacteria and eukarya, let us say, right. Do I have the picture out here? So, here I guess prokaryotes, we see the relatively simple structure, as I mentioned, chromosome not within nucleus or no nucleus. And here you can see the eukaryotes, or one particular example out here, and you see the nucleus, you need to see the membrane, the cell wall, and so on and so forth, right. But again, relatively simpler forms and relatively complex forms, let us say, of life. We are not going to go into that, but again, why do I need to understand this? Because we when we are treating wastewater, we are looking at removal of organic content. As we discussed, we are looking at removal of suspended matter or such, yes. We are looking at removal of pathogens too, obviously pathogens. And if you are looking at tertiary treatment, then nitrogen and phosphorus, the nutrients. So, pathogens. So, to be able to choose a good disinfection process, or to be able to understand the cause for an outbreak of disease, we need to be able to understand at least what are the major pathogens and such. And here we have a classification with size. I believe we looked at this earlier. Bacteria, again this is microns, let us say, micrometers, 0.1 to 10, viruses much smaller, 1 order of magnitude smaller, protozoa relatively much bigger, again obviously eukaryotes and prokaryotes, right. And then again the worms, you can see the big size, and tapeworms, let us say, I guess with respect to sanitation and such, if you have issues, obviously tapeworms. And in that context, obviously we looked at this particular piece of information. Filter sand can strain particles up to 30 micrometers, and we saw that one of the greatest what do we say advancements in health was not due to a medical advancement, but due to an engineering innovation, wherein people started using filtered sand or sand to filter water. That itself removed a lot of or considerable sections of pathogens, let us say, and then disinfection, right. Obviously we have this size out here, bacteria and algae. But what about these viruses? Obviously remarkably small. Viruses, they just have RNA or DNA, and with the corona crisis in vogue, most people are certainly aware of viruses, but again for the sake of providing general information, they have the what do you say replicating what do we say material or knowledge, if I may say so, in the form of RNA or DNA, but they need a host. So humans can be hosts, you have different other hosts, and once they get into a host, they more or less use the host's metabolic process to replicate, let's say. I guess these are layman's terms obviously, but again we have different viruses, let's say. But again, typically with conventional filtration, as you see, we can look at removal of most of the bacteria or considerable section of bacteria and what do we say, eukaryotes, let's say, right, but not the viruses. Let's move on. Until now we discussed or looked at quality, right, and then for example, I need to choose what kind of process and such. I am going to look at quality, let's say. But when I am going to look at what do we say, just quality, I can't really understand the size or come up with designing the size of my particular unit process, let's say, the size of my tank, let's say, and then the hydraulic retention time or so on and so forth. How do I get that? I can't get that information, right. So, for that obviously I need to understand the quantity of wastewater that is coming in and the variation of this particular quantity with what do we say, time, either day, hour or year, let's say, right. So, that is something to keep in mind. In general, I came to know that, or I know rather, that for wastewater, sewage treatment plants in general, we look at a design period for 30 years. So, you are going to look at what do we say, forecasting the population for that relevant area, and then you will get the design what do we say, flow rate or such. But again, how do we get this design flow rate? Let us say I know the population for which I am designing this, okay. I said it is going to be relevant to a 30-year period. So, I need to know the wastewater or volume generated per person, right, person, yes. So, then I will be able to calculate what do we say, the volume for the relevant period or such. Is it per time, per day or such? Obviously, per time is a factor out here. Then I will more or less get volume per time. But the issue is, this particular wastewater that I leave or let out from my home is not going to be the same throughout the day or throughout the year. It depends on the relevant season. People with the garden, obviously you will have much more water usage, people without it relatively lesser, people with what do we say, water closets, large volume of flushing, people with Indian style restrooms or bathrooms, relatively lesser volume or usage, let us say. And then again, depending on class, let us say, you are going to have different what do we say, levels of water usage. So, obviously, it is going to be dependent upon, or the wastewater generation is going to be dependent upon the population, the kind of population, right, and the population too. We will look at why soon, I guess. So, we are going to look at quantity. In that context, I believe we already looked at this. So, this is one graph. Again, please note that this is from the US, but long ago, but again it is pretty reflective. But I guess at that time people were waking up way early, but I am assuming that in India it is going to shift to the right, the graph is going to shift to the right. So, you see that the wastewater generated, let us say, which is this dotted line, more or less is in line with the water that is being consumed, right. Typically in India we assume that its wastewater generated is around 85% of the water that is being consumed, at least in India. But here obviously with habits we see that in the morning, right, the flow rate is higher, right. We have here its units of gallons per day, 1 gallon is 3.7 liters, and then during work day and such relatively less, and again in the evenings it picks up a bit, in the late night and such relatively nil, and then it again increases remarkably, right. So, these are the aspects obviously you need to take into account or understand when designing your wastewater treatment plant. For example, I can't just design for this particular flow rate, right. It is going to be uneconomical, right, and also even difficult to operate. But if I choose a remarkably low value, obviously during this high flow what do we say, time periods, I am going to face an issue, right. So, you are going to typically look at the average while also looking at the peak factor, right. So, peak factor. But in India people really do not look at peak factor, they look at average annual what do we say, flow rates or such, or expected flow rates. But where we see that, or the data indicates that there is considerable variation, and if you want to build a wastewater treatment plant that is relatively more functional and relatively more effective, it's always better to gather the local data if possible and then design your wastewater treatment plant. Let's see, I believe I have some more data out here. Okay, so here we have time in days out here and flow rate measured at wastewater treatment plant on the y axis, right, flow rate. So different days. So here we have our particular what do we say, domestic and industrial flow, right, that's the what you see out here. Let's see, and we see that the minimum is always greater than 0. Well, that's because of infiltration as in steady inflow. Let's see, but if the groundwater table is less, or at least in a developing country like India, chances of infiltration can be relatively less though, at least in Indian context. Let's see, right. So that's something to keep in mind. And then what do we have? Let's say we have a rainfall period out here. Obviously, or mostly in India, you have open sewers. Only now are we going for underground sewers and such. In India, we have combined sewer networks, let's say, right, both for the stormwater and for your sewerage, right, domestic sewage. So a lot of the runoff from the rainfall or rainfall events typically ends up in your wastewater treatment plants. Let's see. So that's why you see that just after this rainfall period, you see a considerable spike in your flow into the wastewater treatment plant, and typically all this waste is relatively diluted. So typically people just let it flow out if the concentrations are within the thresholds. Let's see, right. And what do we have? These we classify as direct flow coming into the relevant drains. Let's say, right. Obviously, general information out here. So total recorded wastewater, estimated or measured bypass flow or overflow. Let's see. So that's a different aspect. Let's see. And then normal dry weather pattern recorded before rainfall, but that's not reached immediately even after the rainfall event. Why? I guess you have delayed inflows, but in the context of India with respect to your high, what do we say, built up area and such, we won't have a lot of delayed inflow, but yes, you will have some delayed inflow, and then after some days or such, again the flow rate is going to come back to normal. But obviously in India, unlike in other countries, we have what do we say, considerable rainfall during a short period of the year. So you are going to have, you know, repetitive events like this. That's what we see out here. So the issue is, do you just design for this particular flow rate or which flow rate, I guess, right. So in this context, people look at peak flow. At least in the US, I believe the design flow rate is the average annual flow rate, but with the rider that the equalization tank, I believe, will be based on considering the peak factor. I believe we have a figure that will explain this in greater detail, pardon me. So Q peak flow rate at the peak by Q average, let's see. So peak, it can be hourly peak, let's say, or the maximum 1 hour flow rate that you saw within that 1 year or such, or it depends, it can be a month maximum, what do we say, monthly flow or such. So typically you will look at that peak factor, and then depending upon your sewage treatment plant's capacity, you will think of adding an equalization tank or not, let's say, right. Let's move on. Okay, with respect to rainfall, let's say, here we have a hytograph, HITO, right. So rainfall and time of day, how much rainfall in millimeters per hour, let's say, right. So that's what we have out here. So considerable rainfall around 10 AM and then again noon, let's say. So if you look at the hydrograph, right, where we have the catchment flow rate, we see almost a similar profile being captured, right. So you can see the relevant profile, the time scale is the same, please note that, right. So more or less similar profile means that the time, let's say, for flow is relatively less, right. So that's one thing to keep in mind. In other cases, obviously the what do we say, time will be typically higher again, but for the same catchment area, the wastewater treatment plant, you see that the peaks are averaged out, let's see, right. Again, that obviously depends upon the flow coming in throughout the day, and also the kind of sewerage network that you have and the kind of stormwater control or diversion what do we say, networks that you have, right. So with that, I will end today's session because I am almost out of time. But in the context of wastewater treatment, we understand two aspects or need to understand two aspects. quantity as in how much water is coming in, and then quality as in the concentration. Why is that? When I look at the quantity and then the quality as in the concentration of the relevant variables of concern, I will be able to get the mass. Once I get the mass, I will apply the mass balance. So, again, as we generally say, everything is about mass balance now, right. So, with that, thanking you for your patience, I will end today's session.